How's everyone doing tonight? Let's see. Hey, everybody. Hey, Levi. Hey, Karen. How are y'all doing tonight? Well, I guess we can get started. I wanted to cover what's going on right now in Kansas as everything just exploded. By the way, I'm doing great. Good to hear you're doing well too, Karen. Hey, JR. Great to hear, Levi. Yeah, target for tomorrow is going to be very interesting. I'll hopefully be able to help you with that a little bit, Levi. It's about as clear as mud, to be honest, but we'll dig into it. Yep, definitely hard. So yeah, you can see tonight has gone just absolutely nuts up in Kansas. And look at this; it just took only, gosh, maybe 45 minutes to go from showers in central Kansas to like basically full on supercells. And you can kind of see that that's happening also down in the southern part of the target area there to near El Dorado and Independence. Those are developing into supercells, and I believe we're starting to get a moisture surge up into that area as well. So these storms should continue well into the night. I don't know how high end the tornado threat will be to start out with, given the moisture situation, but definitely something that will bear watching through the night if you're in Kansas. So with that, let's look at. Let me switch windows here. Excuse me. Just still getting used to this streaming situation. So I'm going to go ahead and share my window here for the web browser. Hopefully you can see that now. Let me go ahead and double check that to make sure that's coming through. Okay, great. So here's the sounding for Norman tonight. So you can see just how close we came to having a really high-end event, particularly with the cells down in southwestern Oklahoma as they were coming into central Oklahoma. You can see that Norman, which is in central Oklahoma, we had pretty deep moisture, roughly around 100 millibars, 125 millibars deep. So that was not that bad. And in terms of the cap, we just had a little bit of a nose at 7 p.m. and a convective inhibition of 66 joules per kilogram, which was actually not that high. So, you know, if we had gotten a supercell with a bit stronger of a mid-level mesocyclone, it's possible that we would have had a very big tornado event tonight. So we missed this by just a hair. I mean, you can see the hodograph. The hodograph shape there is just, pretty tremendous. The typical, side shape, the sickle-shaped hodograph, as they call it, where you basically have that straight section that goes basically due north, mostly speed shear in the, or excuse me, speed shear in the first kilometer that then changes to directional shear above that. And that's absolutely classic for tornadoes. So the fact that we didn't get a really just major supercell through central Oklahoma is a blessing, but it looks like things are starting to heat up to the north. So with that, I can show you where the moisture is now. This is the Oklahoma Mesonet, so it's a little bit more dense as far as the network is concerned of surface observations. And you can see here that the temperatures are, generally speaking, in the mid 60s. And you can see that here in northern Oklahoma, Cherokee is 68, Medford is 66. We have a 71, though, when you get to central Oklahoma. And then down into southern Oklahoma, we have temperatures in the mid 70s. And with that, you have this really high quality moisture that's starting to surge to the north. So 65 dew point there. At Waurika down near Ardmore, we have a 67. And so that area is moving up towards those Kansas storms. So I think for the moment, those Kansas storms are a little bit on the moisture starved side. But as time goes on, this fetch of moisture will head to the north and will begin to become way more interesting. So um, if you care to, this will be a good night to stay up and watch what happens with those storms. I wouldn't be surprised if we had, a large tornado somewhere in central Kansas or northeast Kansas tonight that goes on for a while, owing to this just really tremendous shear environment, low level shear, 0 to 1 kilometer SRH values of greater than 600 meters squared per second squared, which is just unbelievable for any time of year. So very, very impressive. And then that brings us to tomorrow. So this is the outlook from the Storm Prediction Center. The day 2 outlook was issued at 17:30 UTC, and you can see obviously we have seen an upgrade to moderate risk. We talked about this last night, that the probability was fairly good that we would have a moderate risk. I wasn't really sure whether we would get the moderate today or tomorrow, but it looks like SPC just decided to pull the trigger. The probabilities are good for moderate risk verification at least, so they decided to pull the trigger on that risk level. And so you can see that runs pretty much from eastern Arkansas to southern Indiana, kind of a narrow corridor here. And we'll get into what that looks like in terms of the high res models and why that's been painted as the zone of interest for tomorrow. In terms of the tornado threat, that is associated with a 15% hatched risk for tornadoes. And we actually have a significant tornado risk all the way from northeast Texas to almost the Great Lakes up into northwest Ohio. So just a very, very long zone of interest here. And I think there was just some really large population that is, I can't remember exactly what the population size was for the 15%. Oh yeah, 4.4 million people in the 15%. So that would include Memphis, Tennessee, and some of these other cities along the Mississippi River. So very volatile situation, which we'll get into here in a second. Let me just check the chat to see how everyone's doing tonight. Okay, so we have, hi Major, thoughts on 3 kilometer Cape and if it played a role in the lazy cells we saw today? That's a good question. So I guess we can kind of pop back over to today and whether or not having relatively low 3 kilometer Cape or basically low level Cape had an impact on what we saw. Maybe. I think the primary deal was that we didn't get robust supercells. So what I was expecting to happen last night if we had initiation was basically we would get pretty beefy supercells that maybe weren't too low to the ground in terms of the wall clouds and that sort of thing, kind of high based, but they would be spinning really fast. And then as the night wore on and as the moisture advection increased, as we're seeing now, then these storm bases would lower and we'd start seeing tornadoes. But I think what happened is that we started seeing dry air come in from the top of these updrafts and kind of shrink them down to size. If you notice, a lot of the updrafts, I don't know if you saw some of the pictures of the storms tonight, particularly the one up near Enid, Oklahoma, looked very skinny. And whenever I see that, I think about basically dry air mixing in with that moist air and kind of making a skinnier updraft. And I think in that sense, the moisture was a bit diluted, and so you didn't get the full effect of the moisture at the surface, which frankly there wasn't a lot of moisture at the time. So that's my thought on why we probably didn't see robust supercells. I will say 3 kilometer Cape could have played a role in that. We had a cirrus canopy that overspread the area that lowered the temperatures by maybe probably 2 or 3 degrees, which may have played a role in the fact that we didn't get these strong supercells. So we'll see what the other scientific minds think about this and see what ideas we come up with over the next day or so. Hey, Jason, how's it going? And we have another question. This is from BM Tornadoes on the northwest. Random questions on the northwest side of a cell. Is that outflow? I was following the cell that passed through Enid. It may have been. There was another cell on the southwest side of the storm that may have sent out some outflow. I was actually wondering if it was going to potentially promote tornado genesis, but it may have just been a gust of outflow. It may have been a little bit too cool for that to actually improve the tornado odds with that particular cell. So, but yeah, there was definitely some outflow on the southwest side of the storm from a different storm. And then Marcus says the April's Fool's joke was on me. Left Tulsa at 2 on my way to Edmond to stage up when power steering pump went out near Bristow. Limped back in shame. Oh man, sorry about that, Marcus. Well, hey, at least it didn't end up being a huge event. I don't know about tomorrow if you're planning on going tomorrow, but maybe you can rent a car. So sorry to hear that. We've definitely, I've actually, by the way, one of my biggest busts of all time was a date in 2001. This was before I'd even seen a tornado. I'd been chasing regularly for about a year at that point. It was October 9th. I was a freshman in college at the University of Oklahoma, and I went with my buddy to go chase a moderate risk in Western Oklahoma, just a classic situation, negative tilt trough coming in, dew points in the upper 60s to low 70s. We get out on I-40 heading out west towards, a string of pearls, supercells north to south. And we had our pick of the litter. And right when we got to, I think it was the Calumet exit on I-40. I don't know if you know where that is. My friend's car broke down. I think it was like the alternator or something like that. But anyway, we ended up limping to the exit at Calumet and found a place to kind of hang out for about 3 hours until my dad came in from Norman to pick us up. And that day it was like, I think there were probably like 25 or 30 tornadoes. October 9th, 2001. There were about 30 tornadoes in Western Oklahoma, and big, beefy tornadoes too. So anyway, it happens. But we can get back to the business here of forecasting. So let me go back to the top here, and we can talk about the weather at a large scale. We talked about this a little bit last night. Not much has changed. So we'll start with 300 millibars. Actually, this piece was mentioned a little bit in today's SBC discussion, but basically, what we see here is a very flat kind of flow situation, a little bit of a weak trough out west, a little bit of a ridge to the east, pretty classic severe weather setup. You can see that in the dip out to the west and the ridge out to the east. And then in between, you have this nice jet streak up to 100, I think 47 knots is what I found the max to be. This is from the 18Z NAM. And the center of that is in southern Iowa. And we talked about how, from a standpoint of curvature last night, we talked about how if you have really strong curvature, meaning you have like kind of more of a dip in the height field to the west and a ridge in the height field to the east, that where those kind of two come together, you can have rising motion. And that's called ageostrophic curvature divergence. And we really don't see that here. So really the final piece that we'd look for at this level is to see if there's any, rising motion associated with the 4-quadrant model for straight jet theory. So basically with that, you kind of divide your jet streak into 4. So here's your jet streak from Kansas to Wisconsin. So you divide it kind of in the middle across Iowa and Missouri, and then kind of along the axis here. And so the left exit region would be where you'd see really strong divergence aloft, meaning air is kind of splitting apart, and then you'd have rising motion beneath that. And that is associated actually with the low pressure center in western Wisconsin. And then on the other side of it, the right rear side, or the right entrance region, which would be over southwest Missouri and Arkansas, would be associated with divergence aloft as well and rising motion. So actually, looking at this, the only source of rising motion that we see here is in southern Missouri and over Arkansas. So I think that will be a big player actually tomorrow for storms down that way. So something to look out for. And then we can kind of pop down to, I think, let's look at 500 millibars, and we'll look at the vorticity. When I go to 500 millibars, I really like to look at just the vorticity. And the reason for that is we're looking for something called, again, differential positive vorticity advection, which is a big long term for basically where the colored field is moving. And where that is moving, it's going to have rising motion. So um, let's let's examine this. So we can see that the colored field, which again represents vorticity, there's a very pronounced ribbon of vorticity all the way back from the main upper low out in the Four Corners region, all the way up to the Minnesota Wisconsin area. In fact, you can see the brightest colors are in the upper Midwest. And the basic idea here is wherever the wind is pushing that color field out ahead of that is going to have rising motion. So if you're at 500 millibars, you're way above the ground, and something called geostrophic wind is basically going to happen at that level, meaning the wind is going to follow the height lines. So the height lines are the black lines here at 500 millibars. And so you're going to have wind that basically parallels these lines. So basically from, say, southeast Oklahoma all the way up to central Illinois, in this case, following that height line. And so if you can imagine, we have southwesterly winds over Kansas that are pushing that color fill off to the northeast. So anywhere where that color fill is weaker, it's going to have what we call vorticity advection, meaning the vorticity is getting stronger with time. And that's going to be mostly over just Wisconsin and eastern Iowa and so forth. And so you should see rising motion. But what you don't see is a whole lot of vorticity advection at this level down in the moderate and enhanced risk area. If you notice, there's not much color fill at all over this area. So that's actually kind of interesting. There is a little bit of a ribbon of vorticity from, say, Southwest Texas to northern Arkansas. And the wind is, again, going to be from the southwest to the northeast here. So you should get some vorticity advection here. And that actually may be a source of lift for storms that are forming along this, what we call a confluence zone. We'll dig into that when we get to the surface. But basically, there's a surface boundary that's a little bit distinct, it turns out, from the dry line. So the dry line and the confluence zone are actually, 50s, maybe even 100-mile apart. And so very interesting setup here. You often get these confluence zones in southeastern United States setup. So that's a pretty interesting deal there. But bottom line is there's not a lot of forcing at 500 millibars for rising motion. So yeah, that in combination with what we have at 300, I'd say the forcing over the risk area is actually kind of subtle, which is interesting and actually may be good, because if you're looking for, well, depends on your perspective, right? If you're a storm chaser, it's good for, getting more isolated storms, because you're not getting that, just huge, forcing bowling ball low that's causing everything to go up at once. You're getting more subtle forcing, which may actually lend itself more to discrete supercells or isolated supercells, which, if a supercell is more isolated, has its own environment, and it can kind of thrive away from everything else. So that's kind of an interesting fact about that. So we can then dig into the 700 millibar height. This is also interesting. I noticed, let me kind of go down to a regional level here so you can see what's going on. So throughout the day, you kind of see this little bit of this lobe of 700 millibar vorticity that kind of translates to the east, weakens a little bit through the afternoon. This is 21Z, 4 p.m. Central Time. And then by 7 p.m., kind of lights up over here. I think that may be convective feedback from storms that are going up. What I mean by that is within the model, if it's not a very high resolution model like we have here, this is the NAM. And the NAM is kind of coarse. It's kind of low res model. And so it has to parameterize what they say, convection or storms. And what that means is that once you get storms that are strong enough, within the model that in a parameterized sense, not in a real sense, then it basically goes haywire. And I think we're seeing signs of that with these really weird sort of bubbles of vorticity. I think is suggesting that there's multiple storms that the model is developing, but doesn't really know how to resolve that. Um, I think there may be also a subtle 700 millibar wave here. You can kind of see that in southwestern um, Arkansas, where you see sort of more smooth color fill, and so that may be part of the reason that we get these storms, as well as that vorticity is getting pushed off to the northeast. It kind of fires off storms, but once we get to the surface, I'll show you the confluence zone that is present there, and that may be really driving a lot of the convection there. But it's rather interesting to look at. Let me quickly pop over to comments and questions to see if anything has come up. Okay, great. So yeah, yeah, Levi say, I really hope the models are ever convecting this. It's possible. The RRFS has a bit more of a weaker confluence zone, which leads to more isolated development. We'll look into that. So we're looking, okay, yeah, we want to look at Northern Illinois for tomorrow. We'll look at that here in a minute. So going back to the 700 millibar map, bottom line is I do think there is a little bit of forcing for convection, particularly from the zone from eastern Arkansas to southeast Missouri to southern Illinois and into northwest Indiana. I think along that entire axis where that 30% is, there should be some forcing for rising motion. And also, again, don't forget that 300 millibar right entrance region effect that we were talking about earlier. And now, let's, by the way, check out the 700 millibar wind speeds. I think that's one of the most impressive things that I've seen with this. If you look at the wind speeds here, look at that, 70 knots, 69 knots, and if you get up towards the Great Lakes, over 80 knots at 700 millibars. Just a truly, truly impressive wind speed there. And typically, you don't usually see much over 50 knots, and to have up over 80 knots is extremely impressive. And then if you go down to 850 millibars, you can see that kind of the same thing. I mean, my goodness. I like to see at least 30 knots at 850 millibars for tornadoes. And we can see that we have, over 55 knots basically everywhere within the risk area. Peaks over 65 knots in southeast Missouri. And then if you go up to northwest Indiana, you get 70 knots. So not too far off the surface of the ground. I mean, gosh, it wouldn't even take much of basically like a thunderstorm downdraft, maybe from a squall line, right? You take that, high momentum air, and then you just cascade that downward through a downdraft. You can have damaging winds. So even if we don't get the tornado threat realized tomorrow, it's going to be damaging Wind City, with these huge winds. So very, very impressive wind speeds that are projected by the NAM here. And let's see what else. So the 850 millibar moisture situation, which I like to check for just to see kind of how moisture advection is doing. And I really wish we had mixing ratios on this. It's actually just dew points, but you can see dew points roughly 14 or 15 C. And if you actually, I'm just going to go ahead and sneak a little bit of a sounding in here, we can just check out the water mixing ratios. So if you go into this, I think this bottom left, yeah, look at that. Mean water mixing ratio in eastern Arkansas of almost 16 grams per kilogram. And by the way, you're looking good if you have over 12 grams per kilogram of a mean water mixing ratio. So basically, this is like water vapor. Like you think about air you can wear, right? That balmy feeling on a big storm day. The higher the water mixing ratio is, the more balmy it feels. That is insanely balmy air coming up there into eastern Arkansas. I've kind of jumped the gun on the sounding. We'll get back into that. But the bottom line here is just absolutely fantastic moisture everywhere across the risk area. So moisture is not going to be a problem at all tomorrow. And then we'll go to the surface. This is actually where it gets a little bit more interesting. Let's see. So what I wanted to point out here, let me just go ahead and zoom in a little bit. So notice that we have the primary dry. By the way, the color fill is dew point temperature. So what you're seeing here is basically balmy air, very high humidity air off to the east over Arkansas and Missouri and Illinois and points east. And then to the west, you have dew points that are much lower. That's the dry line. And I also checked to see if this was like a kind of a cold front situation, but it's actually, there's not much of a cold front. It's essentially a true dry line, which is a little unusual. You usually kind of see more of the cold front situation here, which tends to lead to more squall lines when you have a strong cold front, but actually it's more of a dry line. So that's one piece that leads me to believe that things may be a little bit more isolated than perhaps the models project. But we'll see what happens. But you can see here a dry line kind of extending from northeast Texas all the way up to northern Illinois. And then what's interesting is you have this like dew point surge into eastern Arkansas. By the way, the time is about 7 I mean, it should be about 7 p.m. Central time here. And you've got, gosh, dew points in the low 70s popping into southeast Missouri and then basically over the entire eastern half of Arkansas. So extremely rich moisture. And what's really interesting is you can see there's a pretty big gradient in moisture going from east to west where this tongue of moisture is coming in. So I think that's going to be a big player in what happens with the storms tomorrow. We'll look into that in terms of high res models here pretty shortly. But I just wanted to point out that we really have, as it were, kind of two boundaries here. We've got the primary dry line and almost kind of this little bit of this confluence axis where the winds are here from the south, and then here they're kind of from the southwest. And so where they kind of come together, that's called confluence. That runs from basically, say, south central Arkansas up through northeast Arkansas, and then really kind of lose a sense of that boundary here in this model, but it's a little bit sharper in some of the high res models. So there's that. And let's see, let's look at CAPE. Okay, let's see what CAPE looks like. Let me go down to the severe weather section. That's not closing, so let's try this. All right. So here's mixed layer CAPE. Generally, you like to see in the southeast, I believe it's about 1,000 joules per kilogram is on average what you get in terms of mixed layer CAPE for tornadic supercells. So the fact that we have generally over 1,000 joules per kilogram over this broad area is very impressive. But we even see in eastern Arkansas up to 3,000 joules per kilogram of mixed layer CAPE, not surface based, mixed layers. So that's extremely impressive type of instability and will lead to very strong updrafts. And you can see that where that moisture surge is happening, we do see higher CAPE. And then to the west of that, the CAPE is a little bit lower. It's not going to prevent tornado development, I don't think. I mean, 1,000 joules per kilogram with the kind of shear that we'll be seeing, we'll look at that here in a minute, there shouldn't be any problems for tornadoes anywhere where you see the color fill. But particularly over eastern Arkansas and into western Kentucky and southern Indiana, I really think there's going to be a pretty amazing event there, either in terms of severe thunderstorms with wind or potentially a tornado outbreak, and we'll see which one that ends up being. But let's see. Let's go to convective inhibition, then we'll jump over to the chat to see what questions that you may have. And this is interesting. So convective inhibition is basically 0 joules per kilogram everywhere. So if you think about the cap, which is the lid that suppresses storm development, and storms try to go up and then they hit that lid and they can't go up. That lid is basically removed by 0Z. And in fact, if you go back in time, we'll go back to 18Z, and you can see that really the cap is removed almost all day. So it would not surprise me at all if we had late morning supercells somewhere across the risk area that produce tornadoes. This is the sort of day where you could, potentially have rogue supercells somewhere pretty much throughout the day. And then sort of the highlight of the event happening kind of towards 7 p.m. and maybe up till about midnight. So no problem for, widespread thunderstorms, supercells. And I think, to me, this is what leads me to believe that tomorrow will actually probably be a pretty significant event. It's really hard for me to imagine that with this much instability, with this high of shear, with basically no cap and subtle forcing, that you're not going to have some supercells that are going to produce significant tornadoes. Like I'm not seeing how that doesn't happen. I think we're at least going to deal with maybe two or three significant tornadic supercells tomorrow, and I think the ceiling is very high. I think the ceiling is the RRFS. I do believe that solution is not unrealistic to think that if you could, and we'll see what that is here in a minute. I keep on referring to that, but it's basically 10 or 12 supercells producing tornadoes. I think that's a possibility. Not necessarily what's going to happen, but definitely within the cards. And we'll see how the atmosphere plays her hand. Let's see about the questions that we might have in the chat. Okay. Yeah, technically a tornado is a damaging wind. Yep, that's true. Just one that spins. Jim asks, could you cover the potential for morning storms and how that might play out, especially with northern extent? Yeah, that's a good question. I haven't looked into that too much, so let's save that for the end, and we can kind of dig into that once we've kind of looked through the main event here. See, there's one more chat here. Okay, great. Thanks, Josh. And let's see. What's next? Okay, lapse rates. This is interesting. Lapse rates are generally above 7 to 7.5 Celsius per kilometer. So, as I mentioned last night, that's pretty decent for a elevated mixed layer. Usually, you like to see, if you want to see a really robust lapse rate, you're looking for something like 8 Celsius per kilometer. And so what we're seeing with 7.5, it's a little bit on the lower side. So that, a lapse rate is basically the difference in temperature as you go up in height. So when we're talking about 7.5 Celsius per kilometer, we're saying that's the degree to which the atmosphere cools as you go up in height. The steeper that is, the higher that number, the greater the potential you have for explosive updrafts. And so what this tells me is that, we have a reasonably strong elevated mixed layer. What's really impressive about this is you notice that orange color, which is, basically over 7 Celsius per kilometer lapse rate, it actually pushes, and by the way, this is happening in the middle levels of the atmosphere. It pushes all the way to eastern Tennessee, into North Carolina, and West Virginia. That's a very far push for an elevated mixed layer. Usually this kind of EML, as they call it, stays out to the west and doesn't really do much in terms of helping the situation with instability. But we actually do see a pretty impressive push of elevated mixed layer. And this is part of the reason we have such strong CAPE. At the same time, because it's not like 8 Celsius per kilometer, typically the stronger that elevated mixed layer gets, the stronger the cap you get. So it's kind of a double-edged sword. So, 8 Celsius per kilometer is awesome for developing extremely high instability, but at the same time, you tend to get a pretty strong cap. So this is kind of a sweet spot, kind of a little bit of a Goldilocks situation where you have enough steep enough lapse rate to where you get really high CAPE, but at the same time, it's not so strong that you have this really strong cap. So this, again, very suggestive of the possibility of warm sector supercells. So we'll be looking into that. So now let's look into soundings for the area. So I'm going to go to, let's see, I've already picked one out. Where'd it go? I think it went away. Drat. Okay, I'm just going to have to pick it again. So I'm going to go kind of up and down the line here. So let's go to mixed layer CAPE, and I'm going to go to Western Indiana to start out with. We can just kind of analyze that from top to bottom here. And so what you see here, this is, let's see where this is. This, I think, yeah, far Western Indiana. CAPE there is roughly about 1,500 joules per kilogram. Let's see, yeah, 1,451. So let's start with the thermo, and then we'll work our way to the right. So if you look at the thermodynamics here, we have a very deep layer of moisture here in Western Indiana. Dew point temperature is 65 degrees Fahrenheit. Very impressive for that far north. Surface temperature is 70, which is not particularly high, but you have a reasonable lapse rate, so you still get quite a bit of CAPE. And then that moisture layer extends at least 150 millibars. So that's actually pretty deep moisture. So that's the first thing I noticed. The next thing I noticed, there's not a lot of cap here. You look at the convective inhibition is 61 joules per kilogram. That's not a problem. LCL, lifting condensation level, basically the cloud base height, that's 381 meters, which basically means you have ground scraping wall clouds, essentially up there in Indiana for tomorrow. So these things are going to be hard to see, to be completely honest. And then there's quite a bit of moisture through the troposphere here that may be, you might have some, high clouds and that sort of thing. And let's see, is there anything else that we want to talk about moisture-wise? Nope. Okay, so, and then in terms of the hodograph, so let's dig into the hodograph. First thing to notice is the extreme storm motion here. Look at that, the right mover here. This is from the Bunker's method defined storm motion. You see you have a 60 knot right mover. That's what the 60 stands for, 60 knots to the northeast. That's from 234 degrees. So from the southwest to the northeast, 60 knots. So that's basically unchaseable. And that's the thing with tomorrow. If you're going up north, you're not going to be able to chase these. You're just going to have to let them go by, which is fine. I've done that before, but that's unless you have like a helicopter, you're not going to be able to keep up with that. So, then in terms of the critical angle, which is the angle between the storm relative wind at the surface and the hodograph, that is a little bit more acute. So you can see the critical angle is 47 degrees. So that's a little bit smaller than we like to see. Usually we like to see the angle between this line, this little blue line, and this little like pink line. We like to see that right around 90 degrees to allow for the most streamwiseness. So streamwiseness basically means that the wind that the storm is experiencing, the inflow that the storm is experiencing, is bringing in a lot of spin. That's what streamwise vorticity means. And it's not so streamwise on the surface layer, but you do see a lot more streamwiseness as you go up in height, particularly as you kind of get into this, half a kilometer area. You see that you start to get, let me just say that the vorticity vectors, so just kind of a little primer again, point to the left of the hodograph. So as you're going up, if you're going to the northeast here on that hodograph, your vorticity vector is going to point to the left of that. So that will be to the northwest, to the north, and to the northeast as you kind of go towards 2 kilometers. And your storm relative wind will point towards the hodograph. And the more parallel that is to the vorticity vectors, wish I had a way to show you that, the more streamwise that vorticity is. So we see, bottom line, a lot of low-level shear. So that's not going to be a problem for tornadoes. That's going to be a factor everywhere. And then you kind of see the wind kind of spinning on itself here. A lot of pretty big weakness from 2 to 3 kilometers. But then you get above 6 kilometers, you start getting pretty good storm relative outflow. I usually like to see, from 6 to 9 kilometers, you want that storm relative wind, basically the distance between the right mover and the wind above, say, 6 kilometers. You want that to be at least 20 or 30 knots. And what the reason is for that is that you want strong outflow at the top of the storm, the equilibrium level and the level, so that you can get, basically these classic or low precipitation supercells. In this case, you might be seeing classic supercells, but you also might get some HPs. You're not seeing very strong outflow, which is a bit of a weakness with a lot of these photographs that I've seen forecasted for tomorrow. So that'll be interesting to see how that plays out. And then in terms of the SRH, which is the storm relative velocity, that's 400 0 to 1 kilometer SRH. So when you're talking about SRH, it's just basically the area bounded by the right mover right here, the motion here, the 1 kilometer vector here, and the surface. So it's basically the area of this little triangle is 400 meters squared per second squared. And basically anything above 100 is pretty good for tornadoes. Above 300 is amazing. 400 is pretty hefty. So definitely some potential for strong tornadoes with this sounding. And that's actually why you have the possible hazard type of PDS, particularly dangerous situation tornado. So no surprise there. And this actually says that we're a little outside the classic supercell line. So you actually, if you, I don't know if you've ever read this little box here, but see that little purple line there, the little purple dashed line. If your storm relative wind is to the right of that, you'd expect more classic supercells. Basically, if your red line was a little bit more over here, you'd expect classic supercells, which tend to be a little bit nicer to look at visually. This looks a little bit more HP, unfortunately, or fortunately. So there's that, and then some analogs, some pretty good analogs. I see May 8th, 2003. That was a pretty big day. And then Topeka, and then the SIGTOR effective layer is 6. You like to see at least 1 for tornadoes, above 3, chance of strong tornadoes, above 5, chance of violent tornadoes. So I don't think this is like, outrageous significant tornado parameter of like 6. I mean, that happens from time to time, but we definitely think that there would be a potential for strong tornadoes with this particular forecast sounding. Okay, let's go back to the chat, see if there's any questions. Okay, back to Northern Illinois. So we want someone to look at Northern Illinois. We can do that. I mean, it's not going to be too much different than what we've seen here in Western Indiana, but we can look at that. So let's go to, did you say Northern Illinois? Let me just double back here. Yes, Northern Illinois. Let's go towards the Chicago area. I'm going to take a drink real quick. Interesting. Okay, so yeah, this is pretty decent sounding in terms of the hodograph. Not all that dissimilar from what we saw earlier in Western Indiana. The only issue is that the thermodynamics are not quite as robust as they are to the east. You see 1100 Cape rather than like 1500, but it's basically the same thing as what you saw in Western Indiana. So a little bit less impressive than what we saw over Western Indiana, but certainly the potential is there for tornadoes there. 493 SRH. So, I mean, you could still get a strong tornado with this. I mean, it says marginal tornado, but with that kind of SRH, definitely a possibility of a strong tornado. Let's go to Western Tennessee, and then we'll dig into this sounding. So this one's a little bit more interesting. So we have way more moisture. Look at that. So 2.68. Wow. And the 76-degree temperature. So it gets you a 2000 Cape, which is very impressive. And then you have the really thick moisture layer, probably at least 200 millibars deep. Minus 43 SEN, no problem. You should be able to get storms out of that. Your lapse rate is a 7.3, which is pretty decent, like I was mentioning. And then we kind of have the same situation, which is basically strong low-level shear, weak mid-level shear, and decent sort of upper-level shear. And right mover is 49 knots to the northeast, so a little bit more chaseable than in Indiana, but not by much. These things will be absolutely flying. And one thing I was going to mention again is that if you look at the storm relative wind, which basically if you take the storm motion here and then draw a line back to the hodograph, that the length of that is the storm relative wind magnitude, and you can see that it goes like 1 ring, 2 ring, 3 rings, so it's about 35 knots at the surface, and then really through the entire layer, it's about surface layer, it's about 30 knots. That's going to be leading to some pretty big storms. So if you do get supercells, they're going to be pretty big out there in Western Tennessee. And then in terms of effective SIGTOR, like 6.5, pretty impressive. A lot of good analogs. So this is screaming tornado potential here. So no surprise there, PDS tornado. And then look at this, interesting, the storm relative wind kind of higher up. We see that red line sort of nosing out into the classic supercell range. So it's a little bit better storm relative winds at the upper levels of the atmosphere. So you expect the storms to vent a little bit better to get that outflow out of the way so that you can have more rain-free storms. So that's actually good for tornado chasing, I think, in general. Let me go a little bit more quickly down to, let's say, southeast, Arkansas, and kind of that bubble of Cape. This is more impressive area in terms of thermodynamics. Look at that, 3,000 surface base cape, almost the same in terms of mixed layer. So 71-degree dew point, very, very impressive. 453 LCL, very low, good for tornadoes. 300 SRH, not outrageous, but pretty strong and definitely supports tornado potential. And then let's see, effective SIGTOR of 7, so very strong potential in terms of the environment. As you can see, it's basically the same everywhere. 48 knot right mover, not that. It's not going to be very chaseable, maybe minorly chaseable if it slows down just a little bit. But you're going to have to, if you're chasing, probably going to do more of the intercept strategy. One way to do that, by the way, is if you kind of get downstream of storms and then kind of move in front of them and kind of let them pass and then go to the next storm in the line and go do the same thing. You can kind of play that game tomorrow, because actually there are going to be a lot of storms that are training along that confluence zone, it looks like. So there's a real possibility you could see multiple supercells and potentially tornadoes tomorrow. Let me go back to the chat real quick and see if there are any questions. Can we show one for Memphis? Sure, we can do one for Memphis. Let's go to the map, and then I promise we'll actually get into high-res models and so forth. So don't go away here. We'll look at that. So Memphis is roughly around here, I guess. And yeah, wow, look at that. This one's looks like a little bit convective contamination. You see those, that omega symbol right here, or the bars to the right. That just means that you have rising motion there. So you might be in a basically parameterized convection, but generally speaking, about the same as what we had in Western Tennessee in general. Not much to say about this except extremely strong tornadic environment. Let's see, in terms of, you might have a classic supercell out of this. So actually, really, if you're looking for chaseable cells, the southern half of the area might be a little bit easier to chase. And also, by the way, the terrain is pretty decent near the Mississippi River and Mississippi River Valley. So that's also something to consider. Okay, let's see. I'm trying to remember where I went from here. Okay, let's go to storm mode. Okay, this is very important. So let's go to the, where is it? Yeah, bulk shear. So this is surface to, I think, 6 kilometers roughly shear, so deep layer shear. And we like to compare this to the boundary orientation to understand whether you're going to have supercell mode or a squall line mode. And really, it's not just this method, but this is the primary method. So you can see here, let me show you how this works. We have wind vectors. If you zoom in on this, the wind vectors are from the southwest to the northeast, roughly around 60 knots. And we want to really compare the direction of those shear vectors to the boundary. So if you remember, the boundary, the surface boundary, the dry line extended from basically northeast Texas to roughly central Missouri and then on up to northern Illinois. So that's perfectly parallel, almost perfectly parallel to the shear vector. So what that means is if the shear vector and the surface boundary are essentially parallel, you're more than likely going to get a line of storms. So along that primary surface boundary, you're probably going to get a line of storms. Not so great for supercells. But again, we have a broad open warm sector, so no capping. So that may not matter at all. You might want to be a little bit east of that, though. And then we have the confluence zone. So let's look at that. So here's that area is a little bit more southwest to northeast. So you can look at the high-res models, and you'll see that there's a definite potential for a squall line along that as the storm, the deep layer shear is parallel to that boundary as well. So with that, I think we can go to the high-res models and we can kind of dig in. Now, I have not looked at the Zero-Z suite of models, so let's go ahead and dig right into that because that's where the fun is. So Zero-Z models are here. So let's start with reflectivity and just kind of jump the gun here. Okay, so what this basically shows is kind of a mess, quite frankly, in the HRRR from northern Louisiana through eastern Arkansas, western Tennessee, on up into the Great Lakes region. I'm not sure that that happens because this looks a little bit disorganized to me, which is a little strange. I'm not really sure how that works, given that we have 55 or 60 knots of deep layer shear. Seems like we'd have a little bit more organization. So I'm not saying that this won't happen, but it seems hard to believe that we won't get at least some storm organization, and we see a lot more of the popcorn variety storms here. Now, ARW, it shows pretty similar picture, except for it looks like if you kind of zoom in on that, I mean, you can kind of see the hints. By the way, these are the high-res models, so they can actually resolve supercells. You can kind of see a little bit of kidney bean structure here and a kidney bean structure here and so forth. So it's kind of hinting at the possibility of getting a supercell there in sort of a line. And then look at that. Yeah, so you can see some more kidney beans on up to Western Kentucky, Western Indiana, Eastern Illinois. So it's interesting that the more isolated area could be further north. So at least according to the ARW, I didn't mean to click on that. Hold on, let me back out of that. And then let's go to FV3 and see what that looks like. And gosh, it's a mess too. So just a huge pile of supercells and line structures there. HRW Nessel showing a similar story. Now look at that. That's interesting. Some nice supercell-like structures at the southern end of that, and then kind of a mess in the middle, and then more isolated structures to the north. So that's kind of been somewhat thematic so far, is that you might have some more isolated modes to the north, and to the south, and the middle might be a little bit more messy. And then very similar for the impasse, and then NAM is not convection resolving. And then there's the 3 kilometer, which actually shows fewer storms. That's kind of hard to believe compared to what we've seen elsewise, but I'll be interested to see if that comes anywhere close to reality. And then you have RRFS, which had a very robust supercell depiction earlier. This is not quite as crazy as the other one, but look at that. Yeah, you see multiple supercells in eastern Arkansas on up through central Indiana. So really rather impressive model there. So it is interesting. I will say, just kind of my gut tells me that there might be fewer storms than it's kind of advertised here. We'll see what happens. I just don't see a very strong indication of synoptic scale forcing for this. So I'm really puzzled as to why we have such a big blob of storms where there isn't a whole lot of forcing. Maybe it's that 700 millibar forcing. One thing I did notice is that if you look at the surface dew point and wind barbs, you can kind of see the, let's see, did it open over here? Yeah, so you can kind of see that the RRFS, I think this is the RRFS. Let's see. No, this is, let me do this one. This shows much less of, or at least in the previous runs it did. Never mind. It showed less of a confluence axis there. So that was maybe why the storms were a little less, numerous in that model. Actually, I can kind of go back to that to even show you what I meant. So in this is the previous RRFS, and you can kind of see here that there, actually, no, never mind. So I'll go past that one. But basically, at this point, it looks like the convection allowing models are suggesting the possibility of a squall line with some embedded structures, supercell structures. And I think that, I don't know why it keeps on opening a new one for me. There we go. I think that it's very possible that we could get some isolated supercells out of this. I would be shocked if we didn't. In fact, look at the HRRR. It's actually just suggesting that these storms are pretty close range, and you got multiple supercell paths through eastern Arkansas, and even one pretty strong one in northwest Missouri, and some other ones across Illinois. And then HRW ARW has a pretty similar signal. And then, gosh, HRW FV3. So I don't know. I'm starting to believe that what this is showing is not necessarily a squall line, but just very tightly packed supercells with maybe some line segments. So we'll see what happens. But if that actually happens, I think we could have a very substantial tornado outbreak tomorrow. But we'll see how if it ends up being more of the linear type, then obviously we wouldn't have that potential as high. But it looks like to me that there's a pretty good signal, at least in terms of the updraft helicity tracks, which show the rotation, that we will see pretty good supercells across eastern Arkansas and then through Indiana. Let me go back to the chat and see what's going on. Oh, yeah. Let's see. All right. So Jim wanted to know about the morning potential. Let's see. Let's go back to let me close out some of these. I have too many windows open. All right. There we go. Oh, yeah. And before I go to the morning potential, I did want to show you this morning's short range ensemble from SPC. And this is like a calibrated tornado potential. And if you kind of go to the 0Z time frame, which is kind of the magic hour, it actually shows this nice 15% probability of a tornado within 25 miles of a point, roughly from southern Arkansas all the way up to western Indiana. So it corresponds very nicely to, of course, what SPC has. So no surprise there. And so what's interesting too is if you look at this, the probabilities actually are not terribly high through the day. So if you look through, like 20Z, excuse me, let me go back. 20Z, that's 3 p.m. Central. There's really not much of a probability at all. But once you get to, like, say, 23Z, which is roughly, or not roughly, it is 6 p.m. Central, the tornado probabilities explode and then really go crazy once you get to 1Z, which is 8 p.m. Central time. So Levi, sounds like you can't leave until after school. Maybe you'll get lucky on this one. So, okay, with that, let's answer Jim's question on the morning storms. So I'm just going to check out, let's go to the HRRR. Is that 3 R's? HRRR. It's easier to say, right? And then we can go to, where's my, I feel like I lost it. Oh, this is the, I'm looking for my, my precipitation. Oh, this is the NAM. That's why. Thought I had changed over to it. It's not. Oh, it's opening up a new window for me. Sorry, guys. Let's see. This is the HRRR. Okay, cool. Let's see. Where did it go? There's the reflectivity. It keeps on opening up a new window for me. I'm sorry, guys. I don't know why it's doing that. I'll have to look into this. This is my wife's computer that I'm using, so it is less user-friendly than what I'm used to. Mine is in the shop right now, and it's opening up a new window for me. And let's see, let's go over here, and let me put it into motion and see what happens. So this is overnight. Oh gosh, supercells overnight, and then kind of a mess, and then a break, and then you see the storms kind of come together in kind of this long line. So, okay, so I mean, basically what this shows me is that, about the morning potential, there's not a whole heck of a lot of morning potential according to the HRRR, which is probably good. Everybody needs a little bit of a break, get rested up for the big day. But it really starts to develop in earnest, it looks like, by 2 or 3 p.m. and then continues through the night and then kind of grows upscale. So, I mean, reading this explicitly, you would say that your biggest tornado threat would be from 3 p.m. to roughly 7 p.m. But maybe if you can keep things a little bit more isolated and maybe a little bit after that. So, okay, I think that just about wraps it up. Any questions that I can answer before we drop here tonight? Let me keep you with a good background image. Oops. Let's go into this one and we'll go back to the chat. Any questions? Any help on a late target? Okay. Levi asks about a late target. Gosh, you're coming in from Nashville, right, Levi? That's going to be tough. I'd say just head due west. If you're leaving after school, you're probably just going to need to go west as quickly as possible and hope you get lucky along the Mississippi River. Okay. All right. Any other questions? Quick thoughts on St. Louis risk. Okay. Yeah. Let's see. Let's see. Let's go back in time. Yeah, there's a little bit of risk in St. Louis, kind of in the 20Z. So that's 3 p.m. time frame. And yeah, gosh, 5% at 5 p.m. So yeah, there's a threat. I would say looks like from the ensemble here, probably around 2 or 3 p.m. through about 5 p.m. Uh, small risk of tornadoes. I wouldn't say it's particularly major. In terms of what the SBC says overall, let's see. Let's go back to their outlook. Yeah, so it looks like St. Louis. Let me bring my cities on here. See if we can zoom in. So St. Louis is right here on the edge of the risk. So, I mean, if this slows down at all, I mean, St. Louis could be in more of in the looking down the barrel of this, but right now it's going to be on the edge of the biggest risk. Feelings on Eastern Ohio late afternoon. I think Eastern Ohio is going to be okay. Looks like most of the action is going to be further west, more towards Western Ohio, along that confluence axis. So I don't think you're going to see too much in the way of severe weather, at least initially. All right. Well, it is 11 p.m. Eastern, 10 p.m. Central, so I'm going to go ahead and call it a night. But I want to thank you all for joining. This is a lot of fun, and if you like, we can do these again in the future. And I'd definitely love to serve you all if that's something you'd be interested in when these things pop up again in the near future. Okay, thanks, JR. All right, folks. Well, I really appreciate it. Just enjoyed talking with you, and hopefully you got something out of this. And we'll talk to you next time. Thank you.